While a new generation of giant telescopes will soon enable us to look ever farther out in space and farther back in time, another new generation of gigantic scientific instruments for exploring cosmic mysteries is going underground. Most dramatically, the Large Hadron Collider at CERN near Geneva will next year begin colliding particles head-on in shattering collisions whose debris may reveal what happened when the universe was born, and perhaps even hint at what came before. Meanwhile, sheltered from cosmic rays beneath a salt mine in northern England, beneath the Apennine Mountains of Italy, in an abandoned iron mine in Minnesota, and in other locations around the world, instruments are seeking to detect the mysterious dark matter that telescopes tell us must permeate and help shape the cosmos, yet is invisible to us. Dark matter has mass, but otherwise interacts only weakly, if at all, with ordinary matter, leading to the nickname of WIMP, weakly interacting massive particle. Some 10 billion WIMPs must pass through you and me every second, and yet we don't even notice a draft. The hope is that very occasionally a WIMP or two may interact enough with ordinary matter to make their passage noticeable in these detectors. Back at CERN, where particle detectors the size of buildings will sort through the fireball as protons collide with protons at near the speed of light, physicists will be searching for evidence of a whole new family of particles, massive but so far undetected partners to the particles in the now well-established Standard Model. These shadow particles, often called sparticles, are predicted by an extension to the Standard Model called supersymmetry, or more familiarly, SUSY. The lightest of these predicted supersymmetric particles could be the missing WIMP of dark matter fame. But finding evidence for SUSY would also provide a powerful boost for string theory. With its notion that the basic building blocks of the universe are infinitesimal vibrating strings, string theory is a controversial attempt to construct a complete, unified theory of particles and forces, including, crucially, the weakest force, gravity. The most head-spinning prediction of string theory is that there are 6 or 7 or perhaps 11 extra dimensions of space, along with the 3 we live within, and that gravity is weak because it leaks out into these extra dimensions. If so, some of the debris from the proton-proton collisions in the new CERN collider might also vanish into these unseen dimensions and so be noticeable by its absence. String theory's prediction of extra dimensions of space fits with the even more mind-boggling idea that there are not only unseen dimensions out there, but also unseen universes. That our universe, vast though it is but one in an uncountable number of other alternate universes. The idea that ours is but one possible universe gets around perhaps its most inexplicable feature, the fact that it is exquisitely tuned to permit our existence. How can this be? If there are multiple universes, then the answer is easy. We're here because ours is the only one, or perhaps one of the only ones, that allows us. But to many theoreticians, this is a simple cop-out, and the explanation for the cosmic fine-tuning lies in some as yet undiscovered fundamental physical law or laws. And there's one last mystery that physicists now feel able to at least consider, the deepest one of all. How did it all begin? Sure, there was a Big Bang, but what caused that? Among the ideas now being considered is this one. 2 3-dimensional universes floating like membranes or brains in higher dimensional space collided. Since that version of the Big Bang, our brain has stretched and expanded. But one day, perhaps in 1 trillion years, it will slow down and collide again. What came before the Big Bang? Another Big Bang, and on and on and on. From the beginning to the end, from the smallest we can conceive to the biggest we can contemplate, physics is poised to reimagine our universe.